Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. So you're designing and building an amplifier using an op-amp, and its gain just isn't what you want it to be. Its gain drops off way too quickly as frequency increases. But you didn't design it that way. Why is that? Well, it comes back to two things that we had to pay attention to when designing amplifiers with real-world op-amps. The first is open-loop gain, and the second is the gain bandwidth product. And that is what this video is all about. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, to begin with, let's talk about op-amp expectations. So here I am. I'm designing an amplifier. I have the basic amplifier, which consists of an input or gain resistor and a feedback resistor. Because the ideal op-amp draws no current into or out of the negative input, the current through the two series resistors has to be equal. And with this truth in mind, for the inverting amplifier, the gain is determined by the ratio of the values of these two resistors. For the non-inverting amplifier, the gain is the same ratio plus 1. Now, there are two assumptions that are often made about op-amps at this stage. The first is that the op-amp has infinite gain. The second is that the op-amp has infinite bandwidth. Now, these assumptions may be just wonderful when we're learning about basic op-amp amplifier design, but in real life, neither of these assumptions is true. This fact does not affect the choice of components surrounding the op-amp, such as the resistor or capacitor values, but it does make a significant difference in our choice of op-amps to use. So let's start by talking about the first of these assumptions. The op-amp has infinite gain. Well, there is no circuit anywhere that has infinite gain, not even the best op-amp. Yes, they often do have a lot of gain available to use, but it is still quite finite. This limit is called the open loop gain. When we talk of a loop, we're talking about the feedback path. It forms a loop. Open loop gain is the absolute maximum gain available with the op-amp, assuming that there is no feedback resistor of any kind. It is an open loop. This measurement is made at DC. It is also known as large signal voltage gain and DC voltage gain, depending upon the data sheet that you look at. In some cases, it's given in dB, and this is easily turned into simple voltage gain with this equation. Voltage gain is equal to 10 brought to the power the dB divided by 20. In other cases, it's simply given in terms of voltage gain, like, well, 200,000. That's nice. In yet other cases, you might find it in terms of volts per millivolt, or volts per microvolt. And you kind of look at that and go, what on earth are they talking about? What is this volts per millivolt, volts per microvolt? Let me unravel this a bit for you. So let's say it's given in volts per millivolt. And they tell you that it is 200 volts per millivolt. So first we ask the question, what is a millivolt? A millivolt is volts times 0.001. Now, we have volts in the numerator, and we have volts times 0.001 in the denominator. The volts on the top and the volts on the bottom cancel each other out. So we're left with 1 divided by 0.001, which is 1,000. So if they're telling you that it is 200 volts per millivolt, This is the same as saying it's 200 times 1,000 or 200,000. So why don't they just say that, 200,000? Who knows? This tells us that we cannot attain a gain in any single gain stage which exceeds 200,000 at DC. Now that we have our first limiting factor in hand, we have to consider the frequency limitations of the op-amp. Every single circuit in the world has its frequency limitations, either by design or by the constraints of physics. The question is, where are these limitations and how can I predict them? Now with op-amps, they have a specification called gain bandwidth product, or GBW, or sometimes GBP, but as the name implies, this is the gain of the circuit times the operating frequency. So if the gain is 10 and we're looking at 100 Hertz, then this product is 10 times 100 or 1,000. The gain of the circuit times the operating frequency will never exceed the gain bandwidth product as given in the data sheet. Now, some data sheets will specifically tell you this, and some will not. Somewhere in the data sheet, there will at least be a graph showing gain versus frequency. Now that I've made your eyes glaze over, what does this mean and how do I use it? Like I said, the product of the gain of the amplifier and the operating frequency will not exceed the gain bandwidth product. So let's see how this affects our amplifier design. Suppose that I'm using an Analog Devices LT1014 op-amp. I look through their data sheet to discover, well, they don't give a gain bandwidth product specification anywhere in their tables. So what do I do now? I start looking for a graph of some sort which will reveal this to me. Here on page 9, I find a lovely graph of voltage gain versus frequency. In fact, I find two of them. One is easier to read than the other, and that's the one I'm going to look at. What I'm looking for is the frequency at which the gain is 1, or 0 dB. Why is this? Because a gain of 1 times the frequency where the gain is 1 is the gain bandwidth product. Let me say that again. A gain of 1 times the frequency where the gain is 1 is equal to the gain bandwidth product. Looking at this graph, I use my calibrated eyeball to kind of scrutinize the lines and decide that the gain bandwidth product for the LT1014 is somewhere around 750 kilohertz. Now that we know this, how does this play out in our design? We want to create a non-inverting amplifier with a gain of 50. We have a GBW of 750 kilohertz with the LT1014 op-amp. Two things determine the gain at any given frequency. The first is the gain as set up with the feedback and gain resistors. This is what I'm going to call the programmed gain of the amplifier, and we will never exceed this number. The second is the gain bandwidth product that we get from the data sheet. At any particular given frequency, we will also never exceed this number. In other words, the gain at any given frequency will be whichever of these is less. So let's go to our example. We have a programmed gain of 50. We also have a gain bandwidth product of 750,000. So at 10 Hertz, the product of the programmed gain and the frequency is 10 times 50, that's 500. 500 does not exceed the gain bandwidth product of 750,000, so the gain of the amplifier is going to be, as programmed, 50. At 10 kilohertz, the product of the program gain and the frequency is 10,000 times 50, which gives us 500,000. 500,000 also does not exceed the gain bandwidth product of 750,000, so the gain of our amplifier will also be 50. But what about at a frequency of 100,000? 100,000 times 50 is 5 million, and this does exceed the 750,000 number from the gain bandwidth product of the op-amp. So now what? Now we employ the gain bandwidth product, which is 750,000. The gain of our amplifier is now the gain bandwidth product divided by the operating frequency. So we have 750,000, the gain bandwidth product, divided by 100,000, the operating frequency, which gives us a gain of 7.5. So at 100 kilohertz, the gain of our amplifier is dropped from the program value of 50 down to 7.5. At 750 kilohertz, the gain of our amplifier will drop to 1. Now, using this scenario, I put together what is called a piecewise model of the frequency response of this amplifier using Excel. And this is what the results look like. Notice the nice flat gain of 33.98 dB, which corresponds to a gain of 50 until we reach a knee point at about 15 kilohertz. And then we start dropping off per the effects of the gain bandwidth product. So you ask, is this really real? Well, for a sanity check, I'm going to simulate this in LTSpice. And so here's my circuit. With a gain resistor of 10 k ohms and a feedback resistor of 490 k ohms, we will have a gain of, well, 1 plus 490 divided by 10, which is 1 plus 49, which gives me a gain of 50. So you can see the programmed gain is 50. I set the simulation to run from 10 hertz to 4 megahertz. I placed the simulated response on the same graph as our piecewise model. The simulation includes some other factors that I don't include in my piecewise model, so the response doesn't exactly follow it. But you can see that it follows pretty doggone closely nonetheless. This piecewise model will give us a general idea of what to expect. But what if I need my gain to stay at 50 all the way to 100 kilohertz, and I still want to use the LT1014 op-amp? Well, what do I do then? When we put all of the gain in a single op-amp stage, the gain starts dropping off at 15 kilohertz. And that is nowhere near my desired 100 kilohertz. By the time I get to 100 kilohertz, my gain is a mere 7.5. So what do I do? The answer lay in distributed gain. So suppose we decide to provide our needed gain of 50 using 2 stages instead of 1, and each stage gives us a gain of 7.071. Why 7.071? Because 7.071 times 7.071 is 50. So with a gain bandwidth product of 750,000, we ask the question, what is the frequency where the gain will drop below 7.071? Now, gain bandwidth product, again, frequency times gain. So frequency is going to equal to the gain bandwidth product divided by the desired gain. So that would be 750,000 divided by 7.071, and that comes out to be 106.07 kilohertz. The gain of each of these amplifiers will not be affected by the gain bandwidth product until we reach an operating frequency of 106 kilohertz. So let's simulate this and see if I'm right. Well, here's my circuit in LTSpice. Now, remembering that the gain is equal to 1 plus the feedback resistor over the gain resistor, the 60.71K feedback resistors with the 10K ohm gain resistors gives me a nominal gain of 7.071 for each of the amplifier stages. With both stages together, this amounts to 49.999, close enough to 50. Now, here are the simulation results placed alongside the results from the single-stage amplifier. Notice how the knee of the amplifier was pushed way out. The minus 3 dB point for the single stage was at 22.5 kilohertz. The minus 3 dB point for the two-stage is now at 129.2 kilohertz. This is 5.7 times the one-stage amplifier. Notice, however, we can't escape the effects of the gain bandwidth product. Both of these amplifiers have a gain of 1 at about 750 kilohertz. So what would happen if we distribute the gain across 3 stages? With 3 stages, the gain of each stage needs to be 3.684, because 3.684 brought to the third power is, well, 50. So here's the final circuit. A gain of 3.684 dictates a feedback resistor of 26.84 k ohms for each of the 3 amplifier stages. And now I place the simulation results for the 3-stage on the same graph as the 1 and the 2-stage. Notice that the knee is pushed out even further. Now the minus 3 dB point is at 242.5 kilohertz. Notice also that the frequency at which the amplifier's gain is 1, well, it's virtually unchanged. While we can push that knee out further by distributing the gain across more stages, you just can't escape the effects of the gain bandwidth product entirely. So how do we select an op-amp with this in mind? Among other things, one of our primary concerns when designing our op-amp amplifier with regard to gain over frequency is the gain bandwidth product. So how do we choose an op-amp with this in mind? Well, the first step is to establish what our overall gain and frequency response requirements are. This will define the minimum gain bandwidth product that we're going to be looking for. We remember that this number determines where our amplifier's gain will be 1. If we are expecting gain that is greater than 1, then this number has to be higher than our desired cutoff frequency. You can use this formula to get an idea of the gain bandwidth product that you will need. The GBW is the frequency of the knee of the response times the nth root of the desired overall gain of the amplifier, where n is the number of amplifier stages that you will be evenly distributing your overall gain across. In order to achieve our desired gain and frequency response, we might have to distribute the gain across 2 or more amplification stages. In fact, if we're looking to have a lot of gain, it's pretty wise to distribute it anyway. For example, suppose that I need an overall gain of 50. Furthermore, I need that gain up to a frequency of 16 megahertz. To do this, I plan on distributing this gain across 3 identical amplification stages. So, what is the minimum needed gain bandwidth product for my op-amp? Well, gain bandwidth product is equal to 16 megahertz times the cube root, cube because I'm using 3 stages, so it's the cube root of the desired overall gain, which is 50. So that gives me 16 megahertz times 3.684 is equal to 58.94 megahertz. Now I go out to the Analog Semiconductor website and use their parametric selector. I have to look at a few data sheets because they list the typical gain bandwidth product in the selector guide. I want to be sure that my selection is based on the minimum GBW, which only shows up on the data sheet, well, if they give it at all. Looking for this information on these data sheets can be quite difficult, and unfortunately, everyone seems to present these facts differently. I end up with an LT1191, which has a typical GBW of 90 megahertz. And you say, wow, that's kind of overkill when we only need a GBW of 59. But this way, I'm sure that the unspecified minimum is within my needs. 2 more mysteries solved: open loop gain and gain bandwidth product. If you found this video helpful, please click on the like and, well, don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-Oots.